Okay, so this example is an advanced example for vector addition. It's going to combine vector addition and resolving vectors. These are very typical types of problems. You'll have some of these on your homework. So when we go through these problems, there's really importance is put on the diagrams. Make your diagrams big, because as soon as you start having to resolve components and add on resultants, if you write your diagrams really small, you're going to be cramming stuff into little tiny spaces. So try and make your diagrams big enough so that you can write. And depending on the size of your handwriting and so forth and the neatness of it, we'll kind of have to judge how big is big enough. So the first thing I want to do is figure out what's going on. So when I read the problem, we're looking at this and it says there's two consecutive displacements. So I have one displacement, and then after I've done that displacement, I go a second displacement here. And then I'm looking for the overall displacement for the plane. Now, even though this doesn't say magnitude and direction, because it doesn't just say magnitude, I have to have a magnitude and a direction in my answer. So you have to be really careful that you don't miss parts of the question. So remember, for vector quantities, if it doesn't specifically state magnitude only, you have to find both magnitude and direction. So the first thing I'm going to do after I've read the problem is draw out these vectors. So the first vector is 75 kilometers, 30 degrees west of north. So there's that two-part direction. So this is saying I ended up west of north. So I was originally going north. So I'm going to pick a point on my paper, and I'm going to draw a little dotted line for north. So that's just my reference. Now I need to end up going 30 degrees west of north. So I'm going to draw a vector that's approximately 30 degrees. Doesn't have to be perfect, but it's me 30 degrees right here. So I'm going to label that 30 degrees. I'm going to label these 75 kilometers. And I'm going to make sure that I have somewhere my compass showing my directions, because it's okay if you rotate your paper and do it in some other direction, as long as you clearly identify where your directions are somewhere on your sketch. So the next vector is going to start where that vector left off, because it's consecutive, one after the other. So this one's reference direction is also north, so I'm going to draw a little bit of north there for that one. And then this time it's 50 degrees east. Now it's okay to kind of over exaggerate your angles, and you don't have to exactly get out a protractor and measure your angles, because we're not adding these graphically. So I'm going to pick something that looks approximately like 50 degrees. And then I'm also 155 kilometers, which is almost double that one. So I'm going to make sure that I double the length of that vector. So that looks like it's approximately double. So this is 50 degrees towards the east of north, and this was a 155 kilometer vector. So I'm looking for the displacement. Remember that the resultant displacement will be the vector drawn directly from where you start, directly to where you end. So you want to add that on to your diagram. And I'm going to label that with a D, because that's my resultant there. You can do an R if you like R for resultant, but D is kind of like a distance. So it's representing that magnitude of that displacement. And then, since I'm looking for direction, I realize that if I'm going to, that's a weird funky angle. And yes, some of you are in pre-cal, and there's probably a law of cosines or something silly like that to do. And you can do that, but that defeats kind of the purpose of understanding this problem. So for the purpose of these problems, please, please, please go through the vector addition method in terms of 2D vectors, because it will help with your process in understanding physics. So I have this magnitude, and I need to find its direction. Well, in order to find its direction, I'm going to have some sort of angle. Well, I can kind of define any angle I want, but I want to have it in something that is in a simple set of map directions. So I'm going to create a right triangle. that is going to describe that resultant right there. So I'm going to call the x component of that dx and the component here dy. So with those dx and the dy, that's ultimately what I'm looking for. And then I'll be looking for this angle theta is what I'm looking for. So I need to ultimately find all of that information. Now, how am I going to do that? Well, the easiest way to do this is to break your other triangles here into their own components. So for example, I have two vectors, and I'm going to label them with a letter. So I'm going to call the blue one vector A. And that's going to help me out here as I go. And what I can do is I can label and resolve vector A into its own components. So to do that, I'm going to make a right triangle. So I can go up here and I can make a right triangle here. And I'm going up and I'm going to the left. So I can label AX and I can label AY. So I could find AX and AY. And then I could also, with vector B here, I can also make a right triangle out of that. Now notice how I'm choosing the angles here that correspond nicely to the ones that are given. I could also draw any other angle, choose any other part of that triangle that I want. For example, I could have resolved this one and done that instead. But that angle would not be 30 degrees, it'd be 60 degrees, so I'd have to make sure I use 60 degrees in my calculations. I don't like remembering to do that, so if I can resolve with my original angle, I will. So then for vector B goes up and it goes to the right. So I have a BX and I have a BY. Now, what I want to do is I want to use these simpler vectors to represent dx and dy. Well, if I look, both AY, oh, I labeled those wrong, haha. BY and BX. So both AY and BY are both upwards. And if I were to take AY and BY and stack them on top of each other, that's what dy equals. dy is going to equal AY plus BY. So if I can find AY and BY, I can find dy. Well, dx is just this portion here, and it knows bx is this huge length, and if I were to subtract ax from bx, I would get dx. So dx is going to be bx minus ax. So that's how I can find those magnitudes. Well, let's take a look. What are those magnitudes? Well, let's look at the triangle for AX. So we have AX and AY. Well, AX is the opposite side of that triangle. So that means AX here is based on sine. So it's going to be A times sine of theta A. Okay. And then AY is going to be A, it's the adjacent side, so it's A times cosine of theta A. For B, BX is also the opposite side, so it's going to be B times sine of theta B, and BY is going to be B times cosine of theta B, because it's the adjacent side of that triangle. And A and B are these original legs, so I can then plug those in and get values. So A is 75 kilometers times sine of 30 degrees. You get 75 kilometers times cosine of 30 degrees. You would have 155 kilometers sine of 30 degrees and 155 kilometers cosine of 30 degrees. And if you calculate those out, AX is going to be about 37.5 kilometers. AY is 64.95. I'm going to keep that extra decimal for now. 95 kilometers. BX is going to be about 118.7 kilometers. And BY is going to be 99.6 kilometers. So I don't want to do too much rounding here early on for those problems. So now I can just plug in here to these formulas. So dy is going to be AY plus BY. So it is going to be 64.95 kilometers plus 99.6 kilometers. Which ends up being 165 kilometers to 3 sig figs. dx is going to be bx minus ax. Bx is 118.7 kilometers minus 37.5 kilometers. So we are going to get 81.2 kilometers to 3 sig figs. So those are the magnitudes. I could add on my vector directions. Dx is going to be towards the east and dy is going to be towards the north. So if I was looking for the components of the resultant displacement, those are my component vectors. But that's not actually what it's asking for. It's asking for the displacement. So that's going to be the whole thing together. So if I wanted to find my resultant displacement, it's going to be the square root of dx squared plus dy squared. So we can plug in, so that's going to be the square root of 165 squared plus 82 squared. Write those out proper. Sorry. Square root of 81.2 kilometers squared plus 165 kilometers squared. And when I plug in to that, I get approximately 184 kilometers. And I'm still not done. I now know the magnitude of my overall displacement, but I still haven't found the direction. So to find the direction, we need to find our angle theta. So theta is going to be the arctan of dy over dx, because tangent is opposite over adjacent. So if I plug in dy over dx, I get 165 kilometers over 81.2 kilometers. Notice that the kilometers cancels out inside of that angle. And when you plug in those answers, you get an angle of about 63.8 degrees. And it'd be like, oh, so we're done. No, we're still not done. First of all, we need to put it all together, and we still need to find our reference directions. Well, we started out based on the angle that was drawn, based on this angle theta, not the whole motion, but based on this angle theta, it is 63.8 degrees north of east. Because I started out east, I ended up north, so it is north of east. So if I wanted to report this final answer, the way I would write that out is I would say that my displacement vector is going to be 184 kilometers at 63.8 degrees north of east. And there you have it. So that's how you solve a problem like that. Noticing the relationship between the component vectors of the two individual vectors that are added together relative to the components of the displacement itself, making sure to have both a magnitude and a direction with reference angles.